Okay, today we're going to continue on with our notes over heat. Today's notes are changes in temperature and phase. So what are we talking about? So if you remember back from chemistry, your phases are your solid, liquid, gas. Okay? And if you think about substances as we either add heat or take away heat, you're going to change phases. The most universal solvent that we use for this example is water. We're all most familiar with water. When the temperature is low, we have ice. When ice melts, it's liquid. And then when we heat it up further, it's gas. So ice, water, or steam. So when we talk about heat and substances, we use what we call the specific heat capacity. And that's the quantity of energy needed to raise the temperature of 1 kilogram of a substance by 1 degree Celsius at constant temperature. Since pressure will affect, we're just going to assume that the pressure is constant for now. So basically we're saying how much energy is needed to change the temperature of something. And it's going to be different depending on the substance. It's different for, let's say, aluminum than it's going to be for water. It takes a different amount of energy to heat up aluminum or water. So how do we calculate it? Well, the specific heat capacity, which is the CP, that P is there to show you that it's at constant pressure. So the specific heat at constant pressure is going to equal Q. Now, Q is the amount of heat that's been transferred. Q is heat. How much heat did you supply or take away? Q divided by the mass of your substance multiplied by the temperature change. Okay? So here it is. If we rearrange this, if we want to calculate how much heat we supplied, it's going to equal the mass of your substance times the specific heat times how much the material changed in temperature. So the change of temperature. This equation and this equation are exactly the same equation, just rearranged. Okay? So, if you look at your equation that you just wrote down, when the temperature increases, delta T goes up. Okay, so temperature goes up, and the amount of heat that you're supplying is going up. So they're both positive. When temperature is going down, your change of temperature is negative because it's cooling off, and your Q, meaning instead of absorbing heat, you're giving off heat. So when temperature decreases, Q and delta T are negative. In the units, T, the temperature, can either be in degrees Celsius or degree Kelvin. You can calculate it both ways, but you must put your units down so if somebody looks at the specific heat number, you're using the right one. Heat is in joules, it's energy. That shouldn't be a surprise. So specific heat is going to be in joules per kilogram per degree Celsius or joules kilogram per Kelvin. Okay. As long as you put the units Kelvin or Celsius and use the corresponding one, you can express it either way. Okay, this table is just a listing of some of the substances we're used to seeing and their specific heat capacity. Okay. If you'll notice, water has a high specific heat. It takes a lot of energy, a lot of heat to warm up water. And water is a substance that takes a while to cool off. So it absorbs the heat, but it takes a lot of heat to get it warmed up. But once it's warmed up, it doesn't cool down very quickly. Let's pick one that's really slow. Gold, okay? This low number tells you that it may heat up fast, but it's going to cool down fast too. Okay, so if the specific heat is how much heat it takes to warm up 1 kilogram of the substance 1 degree Celsius, the larger the number, the harder it is to warm something up. Okay, to determine the specific heat of an object, you have to use a known. So usually we use water because we know the specific heat of water. So the energy absorbed or lost by the water must be equal to the energy absorbed or lost by the unknown. Remember, it's conserved. So if you have two substances that are together, if one loses the heat, the other one's absorbing the heat. Okay, it's a trade-off. And we use calorimetry. Okay, it's an experimental procedure used to measure the heat transfer from one substance to another. And what a calorimeter is, basically, it's an insulated cup. Okay, here's a cup. Yes, this is a calorimeter. Has insulation, styrofoam, there's a cup on the inside. We would put water in the calorimeter, and then we would record the temperature of the water starting out. The idea is if we add something, let's say we add a hot piece of iron or something in this. If we put a hot piece of iron in the water, we have already recorded the original temperature. The iron will lose heat and the water will absorb the heat. So we will record, once the temperature equilibrates, the amount of the temperature change of the water will be the amount of heat that the object lost. Does that make sense? So the iron is going to lose heat. The water is going to absorb the heat. And so we measure the temperature of the water before and after. And then we would plug it in to this equation. So the heat of the water is going to equal the heat given off by X, X being the piece of iron. Yes, it is. It's negative. Because this side's giving it off and this side is absorbing. Because this temperature is going up and this temperature is going down, so it's negative. So Q, if you go back to that other slide, the equation for Q, I said, was the specific heat times the mass times the temperature change of the water is going to equal the specific heat of the material, which we're going to try to calculate, the mass of the material, and the temperature change. And this temperature change is going to be the opposite but equal this temperature change. Okay, so if the temperature of the water goes up 10 degrees, that means that the iron, or whatever the object is that we put in the water, lost enough heat to cause a 10-degree temperature shift, but negative because it gave off heat. So we know the specific heat of water, that's our known. We know the mass of the water because we can measure it out. The change of temperature we measure with a thermometer. We're going to solve for C, the specific heat of the new material. We know its mass. Okay, we can measure the mass and we can weigh it. And the delta T will be the same but opposite of this. And we just saw for C, the C of the material. Okay, so that's specific heat. Now we're going to talk about, in your mind, imagine an ice cube. We're going to talk about the phase change of an ice cube. Okay, so it's going from one phase to another, the solid, the liquid, the gas. The energy required to make it shift to melt the ice cube into water, and then the water being heated up enough to turn into steam. That is the phase change we're talking about. So when you add heat, you're going from solid to gas, and then when you're taking away, you could go from gas to liquid to solid. So energy is either being absorbed or it's going to be either absorbed or given out. So this energy change, it's changing the internal energy. So if you have an ice cube, you supply heat, you're changing the structure of the ice. Okay, you're releasing bonds, you're breaking bonds. The temperature will not change until all of the substance has completely undergone a phase change. Okay, it's a hot summer day. Okay, you have a glass of iced tea. Okay, so you have your tea in here. It may have been a little warm because you just made it, but here's your iced tea. You fill it full of ice. Okay, the tea and the ice will undergo a temperature equilibrium. It will come to a certain temperature. That temperature will stay the same no matter how much heat you apply to this glass. I could set it outside at 100 degrees. All this heat is being absorbed by the glass of iced tea. The tea will not, once it reaches equilibrium with the ice, it will not change temperature until all the ice is melted. Okay, think about that a second. So heat is the energy exchange between two objects at different temperatures or between the two objects of the same temperature when one of them is undergoing a phase change. Okay, just for right now, get it in your notes and I'll try to explain it in a second. Atoms and molecules prefer to maintain a distance from similar atoms or molecules. There's a certain kind of distance they hold to have the lowest energy level. As heat is added, the substance, its particles increase in energy, so they start moving around more. Once enough energy has been added to the bonds holding the atoms or molecules start breaking. This is where your ice is melting, resulting in a phase change or a chemical reaction if enough energy is added. So in your mind's eye, be thinking of what's happening when an ice cube melts. Here the molecules are hanging out. They're in their little lattice. They're frozen. Okay. They may be moving a little bit, but they're not moving very much. Okay. You start adding heat. All of a sudden, these particles start moving around more until the bonds between them start breaking, and you get water. Okay. Here's the point I was trying to make a while ago with the ice trays. Here you have ice, okay? And here it's all ice. It's solid ice. You start supplying heat, and this is your temperature. So I start applying heat. Once that ice starts melting, once the bonds start breaking, you have ice and water, okay? You keep adding heat. You would think the ice water or the water would start getting warmer as the ice melts, but it doesn't. It's counterintuitive. The ice and the water will stay at the same equilibrium temperature until all the ice is melted. And remember, we're adding heat this whole time. And then boom, once the ice finishes melting right here, all of a sudden the temperature will go up corresponding to the heat being absorbed. And then it gets to the point where it's 100 degrees. Now this is when water turns into steam, because remember, water boils at 100 Celsius. So the water will start turning into steam, but the temperature will stay at 100 degrees Celsius until all the water has been evaporated. And then all you have left is steam, and then that steam will start, the temperature of that steam will start going up. Okay? Most people think that it's linear. The more heat you add, the hotter the substance. Okay? If you start out with ice and you start supplying heat, you think that water that's surrounding the ice will continue to get warmer, but it doesn't. The latent heat is the amount of heat to cause this phase change. Okay? It's not linear. This will be on your test. I'll tell you that now. Okay, this is just when you play back the video, this is the key to the chart you just looked at, the graph. So at A, the temperature of the ice increases, but it hasn't melted yet. B is where the ice melts and becomes water, and it stays at the same temperature until all the ice is melted. And then at C, you have just water, and it's free to heat up because it's not undergoing a phase change until it gets to the boiling point. Once it gets to the boiling point, water boils and becomes steam. So it's going to stay the same temperature till all the water has become steam, and then the steam alone will go up. So the places in which the temperature is stabilized is when it's a combination of two phases, the ice in the water and the water in the steam. Energy is required to melt the substance, going into rearranging the molecules of that substance. So we have the heat of fusion. The energy per unit mass transferred in order to change a substance from a solid to a liquid. This would be the heat. The heat of fusion is the amount of heat that it's required in our example to melt an ice cube to water. Okay. The heat of fusion, the energy per unit mass transferred in order to cause a phase change from solid to liquid at constant temperature and pressure. Okay. So the energy, here's the total energy absorbed to cause it. Part of that energy is released in forming the bonds. Okay. So this would be the latent heat of fusion of the water. Energy required to vaporize a substance, okay, and causes the water to go into separating the molecules. That's the heat of vaporization. So in this case, you're going from liquid to gas. The energy per unit mass transferred in order to change the substance from liquid to vapor or from vapor to liquid at constant temperature and pressure. So again, the latent heat, either it be the latent heat of fusion or the latent heat of vaporization. It's the energy per unit mass that is transferred during the phase change of a substance. And again, so energy is transferred as heat during a phase change. It's mass times the latent heat. So if we were going to calculate the heat that is transferred as ice melts or as ice becomes steam, okay, this would be the latent heat of fusion, LF, the latent heat of vaporization. Okay. So here are, I'll go back. Heat is equal to the mass times your latent heat. And again, some examples of latent heat diffusion and vaporization. And take a look at that chart when you play the notes back. And that is it. Get your notes written, get them submitted in Schoology. Thank you.